So good morning. It's a pleasure to have you here again for this last lecture of our mini course. And today we have a guest lecturer, Afonso Bandeira from Princeton University in the United States. Afonso is a very young and very brilliant mathematician. He's still finishing his PhD in the applied math program at Princeton. But he's already got many interesting results. I mean, I particularly like the result he's going to be talking about next week during our conference on random matrices. I mean, the Wigner-type matrices we discussed here in this mini course. And today he'll be talking about something different, which is the community detection problem that I mentioned in our first lecture. So today it'll be more clear what the exact relationship between those inequalities from matrices, right, showing they're close to the expected values. He'll make it clear why that's somehow related to this community detection problem. We said a few preliminary things on Monday, but today you'll see more details about that. So without further ado, Afonso.
Okay, thanks Roberto, and thanks for the invitation. It's a pleasure to be here. Okay, I am going to talk about community detection and about efficient algorithms to do community detection, and you'll see how matrix concentration will play a role. This is meant to be accessible for everyone. If something that I say is not clear, please do interrupt me. I don't know the backgrounds of everyone, so it's difficult to be sure that all of it is completely clear. Okay, so first of all, what is the problem of community detection? So I'm going to pose essentially a random graph model. So the idea is that you have n agents, so say n nodes. And let's think of this as divided into two subsets of n over 2 nodes. So let's say that n is even. Okay, so think about it. So there's n over 2 nodes here. There's n over 2 nodes here. And now I'm going to draw a random graph. And usually the most classical random graph is simply a Nerdish-Rainey random graph where each edge shows up with some probability. Here I'm just going to make the probability of an edge showing up between clusters being different than the probability of an edge showing up within a cluster. So for every 2 points, I draw an edge with some probability. If it's inside the cluster, I draw an edge with probability p. So let's say the probability of an edge being here is p. And across clusters is q. Okay, and I'm thinking of p bigger than q. Okay, what I'm trying to model is a clustering problem where, I don't know, these are people, maybe they are, or maybe they're politicians with different views, and politicians with the same views are more, tend to be more related or more connected, and with different views they tend to be less connected. Okay, and I want to understand for which values of p and q, if I draw this random graph, when can I recover it? Okay, so given n, given p, and given q, this graph is a random variable, and my task is to recover the partition. Right? I look at the graph. Now I no longer know what the partition is. I just see the graph all mixed up, and I want to see when can I recover the partition. Okay, is the task completely clear? Okay, so first of all, let's see for which values of p and q we can hope to achieve this. So the first observation is that, so I don't know if you're familiar with connectivity in the Nerdish-Rainey graph. Okay, is everyone familiar with this? Yes. Okay, so first of all, if p is smaller, if p is much smaller than, say, log n over n, then I claim that it is impossible. Okay, or task recovery is impossible. So what happens, the issue is that if p is much smaller than log n over n, and even smaller than something like log n over n times 2 or times a half over 2 times 2. So what happens is that if p is much smaller than log n over n, actually this graph, this graph is going to be disconnected. It's going to be an isolated point. Okay, and the idea is that each point, the average degree of each point is essentially p times n. Okay, so in this case, will be much smaller than log n, and the fluctuations are of order log n, so there'll be a point for which there will be an isolated point. And if there is an isolated point, there's no way of figuring out which cluster it belongs to. Right? If I have a politician that is not connected to anyone, I have no way of telling which political views it has, for example. Okay? So the first observation is that if p is much smaller than log n over n, this problem is completely impossible. I will never be able to recover the partitions exactly. Okay? So the interesting regime, really, is when p is in the order of log n over n, and q is also in the order of log n over n. Okay? So interesting regime. Okay? So we're going to be focusing in this regime. Essentially what's happening is that, well, if it's below log n over n, you can't do anything, and if it's above, the problem is easy. Okay? So given alpha and beta, we're going to be, we define p and q this way, and we ask ourselves, when can we recover the graph? Okay? So essentially, we should be able to do it if alpha is very far away from beta. The problem should be easier. And in fact, if we had, so what would we do if we had unlimited computational power? Okay, so if we had an unlimited computational power, let's say that we represent a partition by a vector x. So x in our n represents a partition. Okay. Where essential the partition is given by, so xi, say, equal to plus or minus 1, and the plus 1s belong to one side of the partition, the minus 1 to another. Okay? So if I had, given the graph G, so let's say that this is the graph G, so meaning given G, what I should do is simply try to find x that minimizes, or I mean, it's easier to write it maximize. Okay, where A is the adjacency matrix of the graph, meaning Aij is equal to 1 if is an edge of the graph and 0 otherwise. Okay? Okay, let's process this for a second. So I forgot to say, but the lecture notes are on my website online. I should mention this in case you... So let me put it here. And they're here too. Okay, on my blog as well. Okay, so let's process this. Yeah. Oh, you can see it. Okay, okay, sorry. Let me. Okay, or Okay. And they're in both places in you. You see, everything that I'm going to talk about, I put it there. Okay, so what am I trying to do here? Right, let's process this for a second. Let's say that I had unlimited computational power. And what I try to do is just find a partition that better clusters the graph, that has the least number of edges across the clusters and the most number of edges within the clusters. Right, and this is exactly what I'm doing here. The xi's represent which side of the partition each vertex is. The sum of them being 0 is just saying that the partition is balanced, because I started with a balanced partition. And now I'm just, right, every time xi and xj are the same, I win if there's an edge. And if they're different, I'm losing if there's an edge. So essentially, I'm summing the number of edges within clusters minus the number of edges across clusters. Okay, the issue is that, unfortunately, I can't solve this in practice because this is NP hard. But if we could, then this should be what we should try. Okay? And in fact, one can analyze when this particular algorithm works. And this is not the focus of the lecture today, but you can show that. So you can show the following. So let's call this 1. Then you can show that. So let's say theorem. If, and then this example. Okay, so this completely characterizes what happens when the problem is solvable or not, independently of any efficiency of the algorithm. So this corresponds to maximum likelihood. If I was able to solve it, I know that for a certain regime of the parameters, then this actually matches the true partition. And immediately below that, no algorithm can work. Okay, and I'm not going to show this theorem because it's not the subject of the lecture, but it's not conceptually it's not that difficult. What goes on essentially is that you show that as long as for every vertex it has more connections within the cluster than outside the cluster, then essentially this method starts working. And then you just have to evaluate for which values of alpha and beta this starts happening. And notice that this is essentially this is the arithmetic mean, and this is the geometric mean. We know that the arithmetic mean is always bigger than the geometric mean, and it's going to be the biggest the more different alpha and beta are. So it makes sense with our intuition that the more the difference of edge density is, the easier the problem becomes. Okay. So, but the task that we want to do is we want to be able to recover the partition with an efficient algorithm. Okay. And so, okay. First, I'm going to change this a little bit. So I don't want to be dealing with all these constraints, so I'm going to remove one of the constraints. And let's say that I'm trying to solve. Okay, let's say that instead I try to solve this. Okay, so anyone can tell me what the solution for this is? Right, so it's just x being always 1, or always minus 1, because this is positive, so this can never work. I just broke it down completely, right? But I just want to make the problem easier, so like with less constraints, so that it will be easier to have an efficient algorithm. And okay, so this doesn't work, but essentially all I have to do is to put a lot of minus 1s to force the solution with all the signs the same not to be good. And this is the intuition of why I'm going to change the problem a little bit. And I'm going to define B, a matrix B now, which is essentially the adjacency matrix, but is defined as Bij being 0 if I is the same as j, 1 if ij is an edge of the graph, and minus 1 otherwise. Okay? Essentially, what B is equal to 2a minus, okay, simply instead of zeros, I put minus 1s. Okay, and now if I write this, so if I replace a with b here, then nothing changes, right? Because I'm essentially just adding 1 transpose times xi xj, and this is 0. But the thing is that when I replace it here, all of a sudden this degeneracy doesn't happen anymore. And the intuition is that since my graph is super sparse, right, most of my edges are not there. The probability of an edge being there is like log n over n. So most of the edges are not there. Then most of these are minus 1. So there's no point in the x's trying to plot against me by being all in the same, by having very imbalanced partitions. Okay, so this is the problem that we'll set ourselves to solve. But this is just as NP hard as the other one was, and I didn't actually change anything. So what is the idea? So first of all, just a quick survey. Do you know? Does anyone of you know about semi-definite programming and the idea of lifting and relaxing? No? Okay. So this is nice. I'm excited to explain. This is a really nice idea. Okay. So this problem is hard to solve. Let's massage it a little bit. Okay. So this is completely equivalent to the following. Does everyone agree? I mean, I didn't do anything. Okay. Now let me define a big matrix X. Okay. Let me define a big matrix X equals to little x transpose. Okay. Now I'm going to try and write my problem in terms of big X. Okay. So my objective function was x transpose bx. Right? This is a number. I can put a trace on a number. It'll just be the same number. Okay, and I think you see now what's coming next. The trace is cyclic. I can push this xt over there. Okay, and this is just trace. Okay. So all of a sudden, at least my objective value started being linear. Okay, so we're in better shape. Okay. On the other hand, what about the constraints? Right? So xi. So what is equal xi squared? So xi squared is simply the diagonal, the ith diagonal of big X. Right? So what this means is that xi squared being 1 is equivalent to the diagonal of xy being 1, to the ith diagonal of x being 1. Okay? So now I can rewrite my problem. Right? So now I can rewrite, and this should be completely equivalent. And I can write max of trace of bx okay, but it's not all big x's. The big X needs to be of this form, such that big X equals x transpose for some So really, I haven't changed anything. So this problem can't possibly be any easier, right? It's, of course, just as hard. Okay. So, okay, let me erase this part. Let me just keep this, this phase transition. So we know that we should be aiming for something like this. Right? In particular, it's completely clear that if I'm below this threshold, then there's no hope of my algorithm ever working. Right? Okay. Okay, so how can I rewrite, right? This looks messy, right? How can I rewrite this? So I want my big X to be of the form XX transpose, right? Okay, so what do I know about this big X? Well, it needs to be symmetric. Needs to be of rank 1. And its eigenvalues need to be non-zero. Are you all familiar with this notation? I just mean here that eigenvalues are non-negative. And in particular, I'm going to use this notation to mean also that they're symmetric, so that I don't need to spell that out always. Right? So this means that it's symmetric and its eigenvalues are non-negative. Okay, and now if you think a little bit, you see that this is actually sufficient. Right? Because if X is positive semi-definite and symmetric, it admits a Cholesky decomposition. If it's rank 1, the Cholesky decomposition needs to be of this form, just a vector times a vector transpose. Okay. So this means that this messy condition, I can now write it simply as X being positive semi-definite and the rank of X being 1. Okay, so now that problem over there, let's call it, I think I was in 4. So 4 is now equivalent to Is there any question? No. Okay, so again, the problem is equivalent, still just as hard. Right? There's no way I'll be able to solve this in general in a computer. But now the trick is that what we're going to do now is relax the problem. So what we're going to do is come here and go here and remove one of the constraints, the constraint that raises the issues. So it turns out that the rank constraint is the one that raises the issues. If you think about it, all the other constraints are convex. Right? This is a linear objective function. This is a linear objective value. This is a linear constraint. And the matrix being positive semi-definite is a convex constraint. Right? If I have two positive semi-definite matrices, a convex combination will also be positive semi-definite. But this is not true for rank 1 matrices. Right? Just two rank 1 matrices summed together are not necessarily a rank 1 matrix. So what I'm going to do is remove this constraint. Okay? So the problem that I'm proposing to solve is now this one. And now this turns out this is a convex problem, so it has hopes of being easier to solve. Doesn't mean that it is easy to solve. There are convex problems that are still NP hard, but this one is actually easy to solve. The sets are nice and you can solve it. This is known as a semi-definite program. Okay, and it's solvable in polynomial time. So solvable to precision epsilon, so up to arbitrary precision. Okay, you can solve it to something like precision epsilon in time, polynomial in n, time is polynomial in log of 1 over epsilon. Okay, meaning that you can get the kth digit of the calculation in poly k time. And this is what we would like. Okay, so we can solve this problem. We want to solve this one. Well, this one we can't. But this seems to be related. Now the issue is, okay, so I remove the constraint. Why would this constraint be satisfied? Why is the solution of this? Why does the solution of this have anything to do with the solution of that? Right. But you saw Roberto was explaining yesterday the idea of L1 minimization, right? It's sort of a similar idea, which is you wanted to find the sparsest vector that is a solution to some linear system. You can't minimize the L0 norm, so you replace it with something that's convex and nice, and you hope for the best. And you saw a proof yesterday that this actually works in a lot of regimes, and we're going to see that this also works in a lot of regimes. Now, there's some other things that you could do here. And this is the idea of something known as matrix completion, which is essentially motivated by what happens in compressed sensing and L1 minimization. The idea is that you could try to minimize the rank. Right? So the rank is not something we can minimize because it's not convex, but we could minimize the relaxation of the rank. Right? So what is the rank? You can think of the rank, right? So rank of x is essentially, so okay, this is a bit of a side note. So remark. The rank of x is the L0 norm of the singular values of x, okay, or the eigenvalues in this case, since it's symmetric. Right? It's just the number of non-zero eigenvalues. Okay. So you could try, okay, I can't, you learned yesterday that you can't do L0 norm, you just do L1, and you could try to do this, and just try to minimize, let me do with eigenvalues instead. You could just try to minimize the L1 norm of the eigenvalues of x, right? But the eigenvalues of x here are all non-negative. And so the L1 norm of the eigenvalues of x is just the sum of them, and this is the trace of x. So it would make sense to minimize the trace of x. And in general, in problems of this type, people do try to minimize. Not always the matrix is positive semi-definite, so not always it corresponds to a trace, but it corresponds to something known as the nuclear norm, and you can minimize it. But the issue here is that notice that the diagonal of my variable is completely determined. So the trace of x is always n. Right? So there's no point in trying to minimize any of this. So the ideas from L1 minimization don't quite work here. On the other hand, there's something nice, which is that if I'm actually trying to solve a problem in practice, and I use this approach and I solve this, I get a solution x, and I go and I compute, I can check if it has rank 1 or not, right? I can do that very quickly. And if I see that it does have rank 1, then I know for sure that I solved the hard problem. And I know that I have the best possible solution. There's no point in trying any other algorithm. Right? And not a lot of say, heuristics or efficient methods to solve hard problems in some instances have this property, which is sort of a certificate. If you solved it, you know you solved it. Okay, and this is very nice because even though there's lots of algorithms that have guarantees of the type, oh, if your noise is random below a certain level, then you're going to work. This is going to work with high probability. When you're actually solving a problem in practice, it's unclear whether your noise is random with actually that distribution and so on and so forth. So you can't really check the conditions. So having a certificate after the fact is quite nice. Okay, but I haven't explained you why. Why would the solution to this actually be a rank 1? Okay. So let me try to do that now. Okay, any question? In a very intuitive sense, the reason why this has a tendency to be rank 1, this is extremely intuitive. I will give you a proof. But very intuitively, what's happening is that this feasible set is pointy at rank 1 matrices. The same way that if you have a bunch of points and you take the convex hull, and it's just a polygon, then it's pointy in the points where you took the convex hull of. And so if you're solving a linear program, the linear program the optimum will be one of these points. Then here, a similar thing is happening. But it's not true that you will always get a rank 1 solution, because otherwise this wouldn't be NP hard. So only sometimes. So it's sort of a soft version of that phenomenon. Okay, and so the way that what we're gonna show, in fact, is that the solution, so the optimal solution, the actual partition. So let me define G as a vector. So Gi plus or minus 1 that represents the true partition. Okay. And so what is the objective? Task. I want to show that or I guess understand when if x equals to GG transpose is really the unique optimum of 5, then it means I can solve the problem. I just go pick my favorite semi-definite programming solver. I solve that problem. I get x, and it will be a rank 1 matrix. I just take the leading eigenvector, and I solve my problem. Right? So what we want to understand is when is this the unique optimum? Okay, so now we're going to use convex duality. Okay, so I'm going to write the dual of that. So let me rewrite this problem. Okay, and I'm going to write the dual. I want to explain exactly how I build the dual, but I will prove in the end everything that I need about it. So you don't actually have to know any result in duality. I will prove everything. So the dual for this is Okay, so think like Lagrange multipliers. Right, so there is a variable here for each constraint here, essentially, and then vice versa. So z is diagonal, meaning that essentially there's only n variables on the diagonal, and they correspond to these constraints. Okay, that's the intuition. And what I'm going to claim first is that this is true. Okay, this is weak duality. Okay, and I'm going to prove it for you. Okay, so given, okay, so let's call this 6, this was 5. Okay, so given z feasible, or given x and z feasible, six position. Okay, so the picture is the picture you probably learned this for a linear program, is that, well, you can think of the values of the dual and the primal is always below the dual. So if you find a point for which they're the same, then you know they must be optimal. Okay, so let's show this. This is very simple. So x is positive semi-definite, and z minus b is positive semi-definite. The trace of the product of two positive semi-definite matrices is positive semi-definite. So proof. So trace of z minus b okay. Okay, does everyone agree with this? Am I going too slow or too fast, or just the perfect speed? It's good? Okay. Please stop me or tell me to go faster if I'm going too slow. Okay. So because they're positive semi-definite, the trace is positive or non-negative. I mean, you can see this by just expanding it out in the eigenbases, right? If you do just a spectral decomposition, then this becomes clear. Okay. So now let's just write out what this is. Okay. This is trace of z times x minus trace of b times x. Okay, so what is trace of z times x? So remember, trace of the product of two matrices is like taking the inner product and looking at the matrices as vectors. Right? So z is diagonal, so you'll only see the diagonal entries of x. But x in the diagonal is 1. So really, this is the same as trace of z. Okay? So what we just showed then is that trace of z is bigger or equal than trace of bx. Okay? This is known as weak duality. And there's something called strong duality, which tells you that there is always a, if it satisfies some extra conditions, which are actually satisfied in this case, then there is always a pair x and z that satisfies equality here. Okay, but that is not as obvious. Okay. Okay, so what does this mean? This means that if I can find a z such that trace of z is the same as trace of b times GG transpose, and if this, as long as this z is feasible here, because GG transpose is obviously feasible here, right? Each entry of G is just 1 or minus 1, so this will be true, and it's GG transpose is positive semi-definite. Okay, so all I need to do to prove that GG transpose is an optimal solution of 5 is to find Z that matches it and is feasible. Okay, so this is known as a dual certificate or a dual witness. Okay, so you want to prove optimality of a point, you find a dual certificate or a dual witness, right? And that's what we're going to do now. Okay. Okay. So, okay. So let's spell this out. If we can find Z feasible for 6 such that okay? And this was just what I proved there. So if we hope to find such a Z, then notice that then we need this to be the same. So this needs to be 0. Right? So if we hope to find something like this, we will need that trace of Z minus B times GG transpose is 0. Okay? And this is known as complementary slackness. Okay, it's like the complementary slackness in linear program. It tells you that, right? Basically, one of the there needs to be some zeros, right? That's essentially what it's telling you. The constraints and the variables need to. Right. So let me. Yeah, it's not clear how to give the intuition here, but right. Okay. It's very similar to the complementary slackness in linear programming. Okay. So now note that even if we can find such a Z, it is not, right? We just show that GG transpose is an optimal solution of our problem. But we don't want it to be an optimal solution. We want it to be the unique optimal solution. Right? Because if there's lots of them, then we don't know if we can find the right one. In particular, if I replace max of trace Bx by max of 0, then obviously GG transpose is an optimal solution of this, and this doesn't give me anything. Right? So I need it to be the unique optimal solution. Okay, so let's try to make sure that that happens. Let's see how we can force that to happen. And then after we know exactly what we need out of Z, then we're going to go ahead and try and build it. So let's say that we find Z, okay? Let's say that we find Z such that this is true. And let's say that now there's some other optimal solution besides GG transpose. Okay? Then this other optimal solution will also have to satisfy this. Okay? But now so this means that if we ensure that G is the only vector that satisfies this, or only multiples of G will satisfy this, then we make sure that no other solution can be optimal. So what I'm going to claim is that if the second eigenvector of Z minus B, right, so let me put, if the null space, if the null space of Z minus B is simply the span of G, okay, so this is the same as saying that, right? So this is positive semi-definite. So I'm sure that G needs to be in the null space of this matrix, right? Otherwise, this would be positive. And so this is the same as asking that the second eigenvalue of Z minus B is strictly positive, right? We know that it needs to be bigger or equal than 0, but I'm just guaranteeing that there's only the null space of Z minus B has only one dimension, and only G is there. Right? G is there by construction, and I'm making sure that nothing else is there. Okay, so if this is true, then let's say that there was another matrix. So we can say, so if, then let's assume that X, so say that some other matrix X is also an optimum of 5. Then we know for sure that complementary slackness needs to be satisfied. So trace of Z minus B X needs to be 0. Okay, so now we can write just the X in terms of its eigen decomposition, right? Just like we can write X as a sum of lambda i's, vi's, vi's transpose, where lambda i's are non-negative. Okay? And let's say they're really positive, and perhaps I'm not summing n of them, just 1 or 2 or as many non-zero eigenvalues it has. And so now, so now what this means is that, right, so if I do this way, and let's say lambda I is positive, so I'm not sure how many I'm summing, so I'm summing number, right? I'm summing how many non-negative, non-zero eigenvalues X has. Okay, so this means that okay, so I can take the sum outside. And this becomes the same as, right, so I want to write what I'm summing over. Okay, what do I have here? Z minus B, so lambda I, VI transpose, being 0. Right? So these guys are positive. This is a positive semi-definite matrix. Another positive semi-definite matrix needs to be non-negative. This is a sum of non-negative things. So all of them need to be 0. Okay. Okay. And now by construction, only G was in a null space. Right? So this also implies, because this is positive semi-definite, that Z minus B VI is 0. So VI needs to be G, right? Or a multiple of G. But the fact that, so meaning that X is always a rank 1 matrix and is always a multiple of GG transpose. But since I know that the diagonal elements of X need to be 1, then there's only one multiple of GG transpose that can satisfy this. Okay, so if this is satisfied, then GG transpose is the unique solution. Okay, so what we showed is that if this is satisfied, then GG transpose is the unique solution. Of 5. Okay. Okay, so we know what we have to look for, right? So let me just write here the problems again, because I want to erase that part. So this is 5. Okay. Okay, any question? So what do I need to find? So okay, so now what is the task? So we want to show that GG transpose is the unique solution. All we have to find is find Z satisfying all these things. Right? So find Z such that, so Z needs to be diagonal, right? It needs to be a feasible point of 6. Z needs to be diagonal. Let me strategically put this one here. Right? Needs to satisfy this. And it needs to, for trace of z, to be equal to trace of bx. Okay, so this is all we have to do. Given g and our graph, all we have to do is to find z satisfying all these things. Right? Remember that there was randomness in the graph, so our z will have to be random too. And this is where the concentration inequality will come in play. Okay? Okay, so let me rewrite this a little bit. So 2 we know is equivalent. So maybe I should write A, B, C, since I've been calling this the equations. Okay, 2, or B now, is equivalent to asking that trace of Z, this is GG transpose, of course, that trace of Z minus B, GG transpose, is equal to 0. Okay? And this is the same as asking, because this is positive semi-definite, okay, that Z minus B times, write this properly. Okay. And now, because I know that Z minus B has this in the null space, and I know that its second eigenvalue is non-zero, then I can actually remove this constraint. Right? And replace this one with okay. So now it's clear how to find Z. Right? In the way that I pose this, well, Z has essentially n degrees of freedom, and there's n equations here. So it's clear what to do. Okay, so let's build Z. So usually when you build dual certificates, you have to do a bit of guessing. But in this case, the problem is nice enough that you don't have to do any guessing. It becomes completely, the equations tell you exactly what Z you should pick. Okay, so what should Z be? So Zii should be equal to what? Should be such that Zii times Gi minus the ith row, so let me use MATLAB notation. Okay, it's clear what I mean here, I just mean the ith row. V of G needs to be 0. Okay, I'm just making this equation whole. Okay? Okay, so let's think about this a little bit. So Cii is essentially equal to 1 over Gi. So let's think about this for a second. So let's first think about what exactly this is. Okay? So let me write this actually in terms of A. So A is no longer here, but in terms of the adjacency matrix, just because it'll be easier to see. So remember that we defined B was just putting minus 1s instead of zeros. So B was equal to 2A minus 1 transpose minus identity. And this means then that Zi is equal to 1 over gi of now, well, 2 times this. Okay, so let's process this for a second. So G corresponds to my true partition. So it has as many ones as many minus ones. Okay? So this means right away that this guy doesn't matter. Right, so this is, I mean, this is just at entry at row I, 1, G, but it doesn't matter. Like the 1 transpose times G is 0. Right? So that guy doesn't matter. The identity just picks up a GI. So you get a minus GI, but then you divide by GI, you get 1, and you get a plus 1. Okay? So this is equal to 2, 1 over GI. Again, we'll process this in a second. Okay. Now what is this? Given I, for all of the given I, where essentially this vector is telling us, this is a row vector, and is putting a 1 for every edge that's connected to I, and a 0 everywhere else. And if let's say that it's, right, so, I mean, we can rewrite this as 1 over gi, sum over j of aij gj. Okay? If j is in the same cluster as I, then the gj and the gi will cancel. And so essentially I pick up twice the degree, of the degree of I within the cluster minus twice the degree of I across the clusters, because every time the vertex j is in a different cluster from I, gj will have a different sign from gi, and so I'll get a minus. Okay. So what this is the twice the degree, let me call plus, so within the cluster of I, minus twice the degree across the clusters of I. Okay? Well, there's a plus 1, so plus 1. Okay? Okay, let's go back. Okay, I can erase this. Okay, so let's make just a couple of definitions just to clean up a little bit. So, okay, so it's clear what degree plus, what I mean by degree plus and degree minus. So let me define a G plus as the within cluster graph. So this is the graph with only the edges within the clusters, and G minus the across clusters. Okay. And now let's define the degree matrices. So D plus, I just mean the degree matrix of G plus, and D minus G minus, okay? And this is simply a diagonal matrix where I put the degrees on the diagonal. So they're diagonal. Okay, so now we know exactly what this matrix Z is. Right? Matrix Z is just twice of the degree plus matrix, minus twice the degree minus matrix plus an identity. Okay, so now I can write Z. And we're going to try to prove that this Z works. Okay. So what do we need to show about it? So remember that by construction, properties B and A are satisfied. Okay, so all we need to show is D, right? If we show this, we're done. Okay, right? We just reduce it to a random matrix problem, right? This matrix B is a random matrix, right? Z is also a random matrix, right? It depends on the graph I draw, and all I need to understand is the eigenvalues of certain random matrix, right? And now I'll explain how this is actually more than that is a matrix concentration problem. So let's write what this is. So Z minus B, what is it? It's equal to 2 D plus minus D minus plus identity minus B. So B, recall, is 2 A's okay. So this means that this is equal to 2. Right, so there's quite a bit of 2's and minus here, but it should be okay. Right, and the identities, there's 3 minus, so the identities go away, and there's a plus 1 transpose. And this looks a lot like a Laplacian, right? A Laplacian of a graph is usually the degree matrix minus the adjacency matrix. So I'm going to call this the stochastic block model Laplacian. It's not exactly a Laplacian, but it's sort of the Laplacian for the partition. Okay, it's just you take the normal Laplacian, but instead of taking the degree, you take the difference between the within cluster degree and the across cluster degree. Okay, so now it means that remains to show, so we just need to show that L of SPM plus 1 transpose is has a big spectral gap, right, in a way. Okay, this is what we need. Okay, so it's starting to look simpler and simpler. Okay. So how are we going to prove that the eigenvalues, besides, well, there's one at 0. If I hit this with G, right, by construction, this is 0. So there's one at 0, and we're going to prove that all the other ones are bounded away from 0. Okay, so how are we going to do this? Well, the first thing to try is to look at the expected value of this matrix. Okay, so let's compute that. Right? This is a random variable. We're just going to take its expectation. Right? It better be that the expectation satisfies this, because if it doesn't, we're in big trouble. Okay, so what is this? Well, there's a 2. I forgot a 2 somewhere, I think. So this is 2. Okay. So what do we need to compute? We just need to compute the expected value of each one of these things. Okay, so let's go ahead and do it. So what is expected value of D plus? Okay, so for each point, what is the expected degree within the cluster? So let's say for now that there are actually loops, just to make the computation easier. So now there's n over 2 nodes, each within the cluster. Each edge shows up with probability alpha log n over n. Right? We finally got back to the original expression. So this is n over 2 times alpha log n over n, meaning that's a half of alpha log n. Okay? Right? I'm just looking at the average degree of average within cluster degree of a point. Right? And all the points are the same. So it's this times identity. Right? Now, I mean, the calculation is exactly the same for the minus. Simply now, there's also again n over 2 points in the other cluster, but now the probability is slightly smaller, it's beta. So this will be half of beta log n identity. Okay. What is A now? What is the expected value of the adjacency matrix? Right now it depends, right? Let's say, so let me, right, just for visualization purpose, let's say that the matrix is, the partition is done this way. So this corresponds to the plus, say, plus, to the minus. Okay, so this is how I'm just identifying the first vertices with the left side of the partition and the second with the other one. Right, so each edge here is either, so each edge either shows up or not. So there's either a 1 or a 0. And it shows up with probability alpha log n over n, so you have alpha log n over n in every entry, in expectation. Right, and the same thing here. Okay, and they're all the same inside the block, right? Is this clear? So we can actually write this, right, using GG transpose, right? Because note that GG transpose is simply ones here, minus ones, ones, if we assume that this is the partition. Right, so we can write the expectation of A we can write it in terms of GG transpose, right? So first, right, it should be easy to see that this is essentially, so if I do 1, transpose, same thing with ones, so I can write this as a linear combination of these two, right? So in expected value, you see alpha plus beta over 2, so you get alpha log n over n, 1, transpose. So this puts alpha plus beta half everywhere. And then you add alpha minus beta log n over n, GG transpose. Right? I mean, right. So now, if you're within the first block, then you sum them, and you get alpha. If you're with an across block, you subtract them, you get beta. Okay. So this is what it is. Means that now we have an expression for the expected value of everything. Right? So the expected value of 2 LSBM plus 1 transpose is equal to what? It's equal to twice the sum of these things. So essentially this over 2 all go away. Right? And the n makes it go away. So you have alpha log n identity plus beta log n identity. So you have alpha plus beta log n identity. Plus beta minus, alpha minus beta, right? Because it's minus this, sorry. Right, that makes more sense. Okay. Minus the one for A, so minus this expression without the 2, without the over 2 because of the 2 in right in front of this. So you get half. So you get alpha plus beta log n over n 1 transpose plus alpha minus beta log n over n GG transpose. Okay. Plus 1, 1. Okay. So we know for a fact that when we hit G here, it needs to be 0. So there's no point. We can ignore the span of G, right? And we can look in just, so we can restrict ourselves to the orthogonal complement of this, right? Because we know that the random variable for every point when it hits G is 0, so in expected value it also needs to be the case. So we can focus in only what happens in the orthogonal complement of G. Okay, and now I'm going to change colors, and what I'm writing is always in the orthogonal complement of G. Okay, so in particular, what it means is that this guy goes away. Okay, so in the complement of G, it should be clear what I mean in a bit. Then essentially, plus 1, let me change, so, right, I'm going to put this one there, so I get plus 1 minus okay, in the complement of GG transpose, essentially I can remove this term, and this is what the matrix is. Okay, and then it needs to be 0 on GG transpose. So you see that the largest eigenvalue for this, right, the spectrum gap for this matrix, so the second largest eigenvalue. So then this is plus, let me say, some tau GG transpose. So we then get that, so in the direction of 1, 1 transpose, the eigenvalue is of size n, right? Because this matrix has an eigenvalue of size n, and so you get n minus, did I mess up? Yes, this is n over, right. Okay, so this is around 1. This is an eigenvalue of n. So in the direction of 1, 1 transpose, the eigenvalue is n. In all the other directions, the eigenvalue is alpha minus beta log n. Right? So this tells us that the second eigenvector for this matrix is equal to Is this clear what I did? So I have this matrix here. I know that it has G in the null space. Okay? It's something plus a multiple of GG transpose. I don't actually need to look at that because it's a multiple of GG transpose. It will only matter what happens on G, not on the complement of G. And on the complement of G, the eigenvalues of the matrix are essentially, well, there's the alpha minus beta log n in any direction, and then there's a much bigger thing in the direction of 1. So the smallest eigenvalue in the orthogonal of G is of size alpha minus beta times log n. Okay? So this means in particular that, so let me go back here. Okay. I can erase this part too. Okay, so I can rewrite this as, well, the expectation of it minus the fluctuations, or plus the fluctuations, right? So and so what is this equal to? Plus, well, the ones don't matter, right? So the fluctuations here are simply LSBM. Okay. So now remember, everything is 0 in the direction of GG transpose. We don't need to worry about that. So all we need to show is in any other direction, and it's 0 both for this term and this term. All we need to worry about is what happens on the outside of it, and we need to make sure that all eigenvalues are large. Okay? But now we know that this is the case for here. Right? The smallest one of this is at least alpha minus beta times log n. So the only way that and it's essentially the same in all directions, too. So the only way that the smallest eigenvalue of this can go to 0 is if the largest eigenvalue of this is able to beat the smallest of this one. Right? Is that clear? Yes? Or any questions? Right, if I have a matrix, think of this matrix is essentially a multiple of the identity. Right? Think of it as a constant C times identity. And I'm adding another matrix. Okay, the only way that this matrix can now have an eigenvalue that's smaller than 0 is if this matrix has an eigenvalue that's so small or so negative that is able to beat the C from the identity. Right? Because the eigenvalues of this are now C plus the eigenvalues of that. Okay, so as long as the largest eigenvalue, or right, right, so not the largest but the most negative. So as long as the absolute value of the minimum eigenvalue of L, so of 2. LSBM minus expectation of LSBM is smaller than alpha minus beta n over n, then lambda 2 of our matrix that we care about is positive. So in particular, what this tells us is the following. So we can move this 2 from here to here. Okay. So what this tells us is if, so remember that LSBM is a random variable that depends only on the draw of the graph. So if the spectral norm of LSBM minus its expectation is smaller or equal than alpha minus beta over 2 log n. Did I just put a 1 over n? There's no 1 over n. Right. Yes. Okay. Then 5 recovers a true partition. Okay? So at this point, all we have to do is a matrix concentration inequality. So matrix concentration inequalities are results of this type. So you know in a normal concentration inequalities, you have some random variable, and you control how far away it is from expectation, say. So you have a sum of Bernoulli random variables, and you just want to say that they concentrate very well around its expectation. Here, this is done with matrices. So you have some random matrix, and you want to say that it concentrates very well around its expectation in spectral norms. So the largest eigenvalue concentrates very well around. So the difference is bounded in the spectral norm, in the largest eigenvalue. Okay, and so I won't go through the details of how to prove this, but essentially you can use now somewhat standard tools in matrix concentration, and in particular there's an inequality called the matrix Bernstein. It's essentially a Bernstein inequality like the Bernstein inequality for normal random variables with numbers. But for matrices, and the way you use this is by, you can even, it's very parallel to the classical normal random variables case. And this is something, for example, I'll talk about next week, and I think there might be other talks about it next week too. So I won't go into very many details here. But the idea is you can write this matrix as a sum of random matrices, as a sum of independent random matrices. And it's sort of clear here what are the random matrices that we're going to build, right? Because remember that LSVM, right, was D minus plus minus D minus adjacency. Okay? So let's say that I and J are in the same cluster. So same cluster. Okay. Then I can grab the matrix, say, delta J. That is simply 1 minus 1, 1 minus 1, 1, where this is, say, J, and 0 everywhere else. So this is entry J, I, J. Okay? And essentially, this matrix is a sum of, within the cluster is a sum of matrices of this type. Because each edge that shows up, what shows up is something of this type. Right? The A will be this minus 1, because you have minus A, and the degree is on the diagonal. Right? And you'll just sum how many entries show up, right? Because you'll sum for each one. And for things across clusters, you'll be, right, you basically need to put a minus. I mean, it's the same thing, but. Okay, so I mean, this is another way of writing this is EIJ times EIE minus EJ transpose. The same thing, J here. And this will be EI plus EJ EI plus EJ transpose with a minus sign. Right? And so for each edge of a cross cluster, something like this will show up. Right? So this means that LSBM morally and exactly precise, like rigorously, this is true. You just have to be careful what random variables to define. But it will be a sum of I, say, in the same cluster as J, of a random variable, say, let's call it, I don't know, let's say delta ij or gamma ij, which essentially is 1 if the edge is there and 0 if it's not. So we know it's a Bernoulli random variable that was distribution we know of times this plus, or my plus, they are not in the same cluster of some other random variable now with a slightly different distribution because things across cluster are less likely to show up of, let's say I call this prime. Okay. And so what you're controlling in the end is how sums, right, all these things are independent because every edge is independent. So you just have to control how sums of independent random matrices concentrate. And there's an inequality that looks a lot like Bernstein inequality. It's called matrix Bernstein inequality. I have a reference for it in the notes, if you want to see. And essentially, write it this way, you plug it in, and you get that for some alpha and beta, this holds with high probability. The same way that you would get using concentration for classical random variables. Okay, but it's a bit of work because you need to make some computations with them and so on, and there's not much point because it's more or less mechanical. After you have this insight, it's more or less mechanical. So I'll just show you what the result looks like in the end. Okay, and next week I'm sure there'll be talks about this. So it's clear how this random matrix, you can write it as sum of independent. Okay. I mean, it's not surprising. Okay. So let me just see the expression, because I don't know it from the top of my head. So if you use matrix Bernstein, you get that if, so this would be the main theorem, and the proof is completely contained in what I explained, except this part that's pretty mechanical, fairly straightforward. So if if this is the case, then with high probability, so think probability bigger than 1 minus n to some constant, so 1 over n to some gamma. Okay, so polynomially, like the probability of failure decreases polynomial, something of this type. Then with high probability, that is satisfied. Again, so okay, so this is what, if you work out the inequalities, this is what you get. And so let's just compare with, right? What we would like to get is this. It's not quite the same, but it's not so far. Let's see. Note how precise these inequalities are in these results, right? It's not like there's just any constant here, right? The constants are fairly nice. So that's important. Okay, so with a little bit of algebra, if you pick up that expression, Very simple algebra. Okay, this is actually equivalent to something that looks a lot like this. So this is equivalent to, first you need alpha plus beta bigger than 2. What happens is that if this is not true, then the graph is not connected. You would always need this. And so I want to do the algebra. I'm just okay, but I mean, you basically take squares and so on, and collect squares and things of this type. Okay, so this is equivalent to this. So you see, I mean, if alpha and beta are fairly close, right? I mean, okay. So when you think about it, this is a lower order term in relative to this, right? So essentially, what this essentially is that alpha minus beta square is bigger than 8 times alpha plus beta. And here you say that the actual optimal result is with a 4. Okay, I mean, the lower order terms are a bit different. Let's not worry about them for now. And so essentially, what this shows is that the semi-definite programming approach provably works almost right to the information theoretical threshold. Below this, nothing can work. So it works almost all the way down to that. It's just a factor of 2 away, in a way. In a sense, it works exactly almost to the regime, order-wise to the exact same regime. Okay, and so yeah, so this was the main theorem that I wanted to show, and the proof, and I wanted to motivate the workshop next week by showing how matrix concentration has so many uses, right? Yesterday you saw things for sparse recovery, and it's a completely different problem. And in the end of the day, all you have to do really is bound the spectral norm of some random matrix. Okay, so now that I have like 20 minutes, I'll take 10 to explain 2 things that are not exactly related to, or that's marginally related to these things. Okay, one is on again this stochastic block model. So there's an interesting, and this if you want references, you can email me and I'll give you references. But there's some nice things in the, so let me go back there. So let me see, because I don't know the expression from the top of my head. And I want to give the right phase transition. So you can formulate this problem in a slightly different way. Okay, and now I'm not going to actually do any math. I'm just going to describe things and wave it. Right, another interesting problem is you say, okay, maybe I don't want to recover everything. Maybe I just want to recover some of the points. Okay, maybe all I want to do is just have a guess that beats random. So it's very easy to get a guess that gets half of the points correctly. I just output all of it being 1, or just a random guess. Let's say that I want to do slightly better than random. So let's say that I want to do a half plus epsilon for some epsilon. Okay, the question is, when can you do this? Okay, now it's not clear that the log n is needed, because in a way the intuition for why the log n was needed is because otherwise those isolated points, and you can't say anything about them. But I mean, it's fine if we can't say anything about some of the points. All we want to say is something meaningful about most of the points. So it turns out, so this is known as partial recovery. And it turns out that if you want to beat random, you can do it in a much sparser regime, on which P, so partial recovery, the right regime for partial recovery is A over n, and Q being B over n. If you're below this, right, you essentially have no, the degree is always 0 almost, but this then the average degree is like A and B, so it should be the right regime. And in fact, people from some physicists some years ago conjectured that they made some bold conjectures. They conjecture that in this model, if a minus b squared bigger than 2a plus b, something like this, just make sure. Yes. So I didn't explain exactly where should I explain. In a way, right? You saw that this in a way is my bound here, and this term will be a sort of a variance for the problem. That's why it shows up on this side. And here is the same thing. This is sort of the bias, and this is sort of the variance intuitively. So these people in physics made this physicist made this conjecture that if this is true, then partial recovery is possible. And moreover, efficiently. You can do it with an efficient algorithm known as belief propagation. I don't know if you ever heard about it. No? Belief propagation is a cool, okay, let me explain this, and then if I have 2 minutes, I'll just say a few words about it. So the physicists use this, they have these techniques in statistical mechanics and so on of coming up with conjectures. And through some calculations, things known as the cavity method and things like this. And they're not rigorous, but they very often give the right answers. It's quite mysterious. So they conjecture that if this was the case, this was possible, and otherwise, so if, I'm not quite sure what happens at equality, but if this is true, then it's impossible. Okay. And indeed, throughout the years, and the last one was probably a couple of years ago, a series of papers proved this conjecture. So the physicists were correct. So you can actually show that if all you want to do is partial recovery, you don't need the log n, and this is exactly the phase transition, and more so there's an efficient algorithm, which is not based on semi-definite program. Is you can do one of two things, either a spectral method, so just take the top eigenvector of the adjacency matrix and try to see what the second, and try to see what is the clustering from there, or use something known as belief propagation. So belief propagation is maybe I won't venture to explain it. You should read about it. It's something quite mysterious because you make a ton of assumptions that are wrong, and then on top of that you feed it completely wrong information, and then in the end it gives you the right answer. It's sort of like, right, there's another method for which you put garbage in and you take something out, which is the power method. Right? If I want to compute the top eigenvector of a matrix, I can just, I just take a random vector and I hit the matrix against that vector. And then I normalize, I hit it again, and so on, and this will converge to the top eigenvector. Right? At least in some conditions. And essentially what you did is you put garbage in because you put a vector that might not look nothing like the top eigenvector. And essentially what's happening is something like that, but it's a lot more mysterious. I recommend you take a look, and it's interesting. So okay, so this is sort of what motivated looking even into the exact recovery. This is what came up first. And so the other thing I can mention in 5 minutes is there's another way of analyzing this semi-definite programming relaxations. And I don't know if you're familiar with the max-cut algorithm, the algorithm to solve max-cut. Oh, okay. So I won't explain that, but I'll put the reference on the notes, and I think it's a very easy to read paper, and it's very nice. And the idea is, in a nutshell, the idea is that you might be interested in understanding what this semi-definite program relaxation is doing, not on a random instance on which you'll actually be able to solve the problem, but on any instance. So in a worst case type of analysis. So in that case, you cannot hope that the solution of, say, this problem will always match the solution of the problem you want to solve. And so what you can do is you solve this problem. The solution will be a matrix that is not necessarily rank 1. And in particular, you can write max cut as a problem of this type for a particular B, right, with the extra rank constraint. So you solve it. The matrix is not necessarily rank 1. And then you do a rounding step. or a projection step. So in that case with the randomized algorithm, but it can be with any rounding algorithm, you grab the solution of this, which is not rank 1, and you round it for something rank 1 that is a solution of the original problem. And then you guarantee that as you round, the objective value doesn't change very much. Or you control how much it changes. And this gives you an approximation algorithm for the original problem. So you grab the original problem, you relax it, and then you round. You control how much you lost in the rounding. And this gives you an algorithm that you know has some optimality conditions on the original problem. It's at least some fraction, say, of optimum, or at least close to the optimal solution in some way. Right? And this has been, in theoretical computer science, people do this kind of idea a lot, because it's, right, they're much more interested in what happens on worst case instances. And there's lots and lots of approximation algorithms that are based in this idea. And the max cut one is particularly nice. It was one of the first ones and is quite remarkable, and the analysis is super, super simple. I really recommend taking a look. Okay, I think that is it. If you have any questions, more than happy to answer. Yeah. Mm-hmm. Right. Mm-hmm.
And this G is the partition that is deterministic. It's not a...
Yes, say, yeah.
So how do you relate the...
So the Z, right, so the partition, the Z that you build depends on both G and the graph, right? And I don't know if I have it here anymore, but Z was equal to something like D plus minus D minus plus some identity or something like that, right? And so essentially, D plus and D minus depends both on G and on the graph, right? Because what is a plus and what is a minus depends on G, and what are the degrees depend on the graph. So it's in this way. Essentially, the dual certificate you build depends on both the instance of the problem, so it's G and the randomness from the graph. And this is what allows in the end for the problem to be a problem of controlling random variables. And in lots of these, so in lots of these, so there is an extra difficulty that doesn't appear in these problems that very often it shows up, which is sometimes you actually have a choice of which dual witness to pick. And then it becomes, it becomes a bit trickier. But in this case, you just, as I see, you work it out, and you see that Z is something that depends now on the partition and on the randomness. And you just have to show that it satisfies the properties. Any other questions? Okay, all right, thanks.